Swayam Prabha. Digital India. Educated India.
Welcome to the subject Advanced Digital Image Processing and Computer Vision. So, we are discussing about different properties of projective transformation, and we will continue this discussion. Using the properties of projective transformation, we can perform certain correction in the images which will remove the distortions due to projection. So, particularly the distortion that the parallel images which was from a source image which looks parallel in the Euclidean sense, after projection, after projective transformation, you can consider that they are converging. So, that is the general thing. Say this in this image, these two parallel lines, they do not look like parallel after we apply this transformation on this set of points. Now, when we have this observation only, I do not have this source image, can I get back this image? Now, one thing we can do, instead of getting back this image, what we can do, we can make this edges parallel in the Euclidean sense. Now, we may not be able to preserve the angle, like the angle here. As you see, due to projection, this angle itself is not rectilinear and not 90 degree here for the rectangle. But what we can perform that we can make those edges parallel. So, these two edges becomes parallel. Similarly, if I consider say this edge and this edge, okay, so this edge and this edge are parallel, and these two edges are parallel. So, we can make this kind of rectification. For that, what we need to do, we can design a transformation, another transformation, which will effectively perform the, if I consider the multiplication of these two transformation as a cascade of this, that means if I perform HP prime HP, it is effectively, it will become a affine transformation, affine projective transformation. So, since it is affine projective transformation, as we know that in affine projective transformation, parallel lines still remain parallel, though their direction changes and also angles are not preserved. But effective after applying HP prime on these images, we can make that thing. So, how do you compute this transformation? Now, which itself is not an affine transformation, which is some sort of projective transformation, but multiplication of these two that can make it also affine transformation. And once it is affine transformation, then again if I multiply with any other affine transformation, then also it still remains remains as a affine itself. So, let us see how we can do these things. So, one of the thing what we can notice here, say when these two lines they become intersecting, they intersect at the vanishing point, that we know because these two lines are parallel. So, they intersect, say these two lines are parallel. So, they intersect at the vanishing point. Similarly, these two lines also will intersect a point which is also vanishing point. Now, vanishing points are the point of intersection of these parallel lines which are ideal points and mapping of ideal point through this projection matrix. We have discussed that. So, these vanishing points, they lie on the vanishing line. Now, we know that vanishing line, it is actually a transformation from the line at infinity. So, this transformation would be, say if this is the projection HP, now you should understand HP is not known to us. So, theoretically we are considering HP because we are observing this one, we do not have the original image just from the observations, but we understand there is a projective transformation that took place. So, for that HP we can perform transformation of the line at infinity, which will become the vanishing line at this stage. I mean this is vanishing line L. So, which will become L at this point. So, from the image itself we can compute L because the L is the cross product of these 2 points. We can compute first vanishing points and then from the vanishing points we can compute L. So, you note that this vanishing point is cross product of these two lines. Suppose I consider this line as L1 and say this line as L2. So, this point can be computed as L1 cross L2, and suppose this line is L3 and this is L4. So, this point can be computed as L3 cross L4. We have seen these things. So, now again, if these 2 points, if I consider this is a vanishing point for this, say BP2 and say this is BP1. So, this line L, this should be equal to BP1 cross BP2. So, this is how you can compute all these things. So, once you compute it, this vanishing line, and which we am again showing with this subscript infinity. So, I should write it like this, and this is the line at infinity actually, and this is the function. It is not the exact expression. You know that it should be transpose of HP inverse into this line at infinity, which is 0, 0, 1 column vector. So, now if you have this vanishing line, now there is a transformation which can make convert this vanishing line. That means, I need a transformation HP prime such that this line should be mapped to 0, 0, 1, which means this transformation should be HP prime minus transpose L infinity. So, I have to get that HP prime which can map to this. Now, it can be shown mathematically, it can be shown if I take this transformation in this form. This is minimally, and as I mentioned that any affine transformation after that will always preserve the line at infinity at 0, 0, 1. So, we will always preserve that line at infinity. So, I can multiply with any other affine transformation. So, whose form, as we know that whose form would be that last row would be 0, 0, 1, and here some elements this matrix is called A and this matrix called T. Any element A and T would be fine. So, any arbitrary affine transformation will do, but minimally I have to first make this transformation to bring the vanishing line as line at infinity, and this is shown. So, we can see that for, as I mentioned, for any affine transformation. So, this is a relationship, as I mentioned, that if I apply the transformation HP prime on that line, which means I have to multiply with transpose of its inverse, then I will get 0, 0, 1. You can check that part. You can take this inverse, take this inverse and then transpose it and then multiply with this, and you will see that you will get 0, 0, 1. And once you get this, then what happens that because the line at infinity still remains at 0, 0, 1. So, all the intersection points of these lines, they are ideal points, which means after transformation these particular lines, they become parallel in the Euclidean sense. So, what should be the algorithm? Algorithm should be, in this case, that we consider any observed image. This is, you see that this is the observed image where the source image is not known to me, what transformation takes place is not known to me, but we have only this observed image. From there we can understand that these lines are actually it is parallel in the Euclidean sense in the original image. So, we can compute its vanishing line. Suppose this here we have considered these lines, say this is L3 and L4, then we can compute its vanishing line as cross product of L3 cross L4. This cross product of these two vectors. Similarly, you take these two lines, which also we understand they are parallel in the original image in the Euclidean sense, and there if you take the cross product, then you will get V1. So, you get this point from these two lines. And finally, the vanishing line that you need to compute, which would be the cross product of V1 cross V2. So, once you get this vanishing line, then you can always transform you can get the transformation from this itself, as we have shown. It would be like 1 1, then 0 0 0 0, L1 L2, L3. So, if this is equivalent to the column vector L1, L2, L3. So, this is what you will get. So, now this transformation you can apply on the points and you can get the images. So, I will just show you an example. In this case, I have taken a bigger image of parallel lines, because in the last example I have just taken it from Gisserman's book and Hartley and Gisserman's book, and from there I have shown you those two typical configurations. But let us consider another example. So, this is a painting of an image, and as you understand, the sides of that frame, these are actually they are parallel, actually they are rectangular also. But now when you take the image, then this projection takes place, and you can see at least these two are very conspicuously are converging, though these two lines are not very conspicuously converging. They looks like parallel, but still they are also converging at a larger distance. So, so what happens that now using the same technique, I can make an interactive interface by which I can pick up those parallel lines by picking up endpoints itself. So, suppose these are two, I have basically selected two endpoints, and then from those endpoints I can also compute the parallel line. So, I have actually picked up the points instead of drawing lines. That makes my job easier. So, you see that this is one line out of them, probably this line, and this is another, this line is this one, take the cross product. Then this is another line, and this line will give you the second line L1 and L2, and if I take the cross product of L1 and L2, then I will get its corresponding intersection point. Similarly, I will choose another two parallel lines by choosing the endpoint. So, I will get those two lines L3 and L4, and then accordingly I will compute the respective vanishing point of L1 and L2, and also vanishing point of L3 and L4, and then the vanishing line would be again cross product of V1 cross V2, and which is shown here. You can see that the scale is a very large magnitude is there in the scale, and this is the part which is shown in this form. One of the things you should note, actually these numbers are large because the coordinates are very large. So, the transformation that we get in the previous examples, the transformation is that if I apply a transformation H, then what will happen? Then you will get the resulting transformed image, where you will find that these edges they became parallel. Also these edges. So, all seemingly parallel images which were there in the original image, they still remain parallel, but though it could not recover the rectangular relationships of these of this particular, that means that it could not preserve the angle and it could not form the rectangles with the sides, because affine transformation that do not preserve the angles. So, this is called affine rectification. Now, let me discuss that the properties of projective transformations on conics. So far we have seen that in a projective transformation, as you know, by definition a point is mapped to another point, that is the projective transformation. Then a line also gets mapped to a line, again by definition itself, because that is the property of projective transformation, that collinearity should be preserved. Now, what happens to conics? We discussed about conics earlier in projective geometry, and if you take the representation of the conics, as you can see that it is a quadratic expressions with the coordinates ax square plus bxy plus cy square dx plus ey plus f. So, a, b, c, d, e, f, they are the coefficients of this representation, and in the homogeneous coordinate representation, this becomes much more regular and simple, convenient, because what we can do, instead of representing with just x and y two coordinate values in the real space, we will take the third scale value also and use it in the homogeneous representation. So, when it becomes an element of the 2D projective space, then this expression is equivalently could be written as a quadratic expression in this case, and it is X transpose Cx equals 0, where C is a 3 cross 3 matrix which is a symmetric matrix. So, this is how the C is given, as you can see that this matrix C, which is actually describing the conics, and there are 6 coefficients, but since if I multiply all the coefficients by a scale k, still it remains the same conic. So, it is an element of the projective space that we discussed earlier. So, there are 5 independent parameters, because all of them you can express by fixing one of them as a ratio of that. So, this matrix 3 cross 3 matrix, there are actually 5 independent parameters. So, there are this degree of freedom is 5, and we can see that how it is a symmetric matrix here. This we have discussed earlier. Another thing also we have discussed that this is a point conic description, but same conic can be also described as an envelope of their tangents, and say tangent is described by a line, once again that is an element of the projective space, and same conic can there exist another say C prime or C star we say, and L. So, this is also in the same form, where this is called the dual line conic of C, and there is a relationship between C star and C, which is basically C star equal to C inverse. So, these are the things we discussed. Now, the first question that we would like to see, that if I transform the points on a conics, so what arrangement you get in the transform space. So, that would be interesting to observe. So, let us see what it is, what we are getting, right. So, as I mentioned, so these are the things for the conics, that the dual conic description, and this is the relation. So, once we transform a point like x using a projective transformation H, which become x prime. So, if I consider all the points which are on the conic and how their transformation, what arrangement you get. Now, there we can find that we can replace this x by H inverse x prime. This is also H inverse x prime, and then by simple algebraic manipulations, because you know that if we have transpose of multiplication of two matrix, then we can write it as B transpose A transpose. So, you can apply them here. So, you can see that this is x prime transpose, this is H inverse transpose, C remains similarly, this is H inverse and this is x prime. Now, you observe this thing. First thing is that this is a 3 cross 3 matrix. This can be considered as say C prime itself. So, you have x prime transpose C prime x prime equals 0. So, it looks conic, only thing is that this C prime also has to be symmetric. Now, this kind of operation, like if you have any symmetric matrix and if I multiply the symmetric matrix with this, with a 3 cross 3 matrix like with a transpose and here the matrix, then also we can show that it remains symmetric. Now, this is a mathematical property. So, which means C prime is also a symmetric matrix and it is a 3 cross 3 matrix. So, which is a description of a conic. So, that means that from the conic in the conics in the original space after transformation still remains a conic. Of course, its parameters or its parameter values, they get changed. The shape of the conics also get changed by this transformation, but it is also in the class of conic. Okay, so this is our summary of your discussion, that this C prime, which is given by this, that transpose of H inverse, then C and H inverse, if I multiply them, then this becomes a transformed conics. Similarly, I can get also the it also defines the dual conic, because if I take the C prime inverse, this means that I am getting the H minus T, that is the transpose of H inverse, C H inverse inverse. Now, you know, once again, like transpose, if I do AB inverse, it would be also B inverse A inverse. It get, so this can be equivalently written in this form. So, I can write it as, say, this H, then C, and then this is H transpose. Okay. So, this C is C inverse. So, what is this C inverse? C inverse is once again the dual conic of C, dual line conic of C. So, by the same transformation, you get also the dual conic which is consistent. So, it is also dual conic of this one. So, this is also the dual conic of, so if I write sister, so this is a dual conic. So, C prime and dual conic of it would be also the same, which is actually the C prime inverse, which we have mentioned. So, this is the, you know, in a cleaner form we can see here that relationships what I was explaining. Now, there is one particular interesting feature for conic is that I discussed about these circular points, if you can remember, and these are the two circular points, that is one I 0, this is a projective point and it is an ideal point, if you can see that scale is 0, but the peculiarity here is that these values is a complex number. So, this is represented in a complex space, complex projective space, and this I is actually root over minus 1. So, this I is root over minus 1. And we have discussed that under similarity transformation, the circular points is a fixed point of similarity transformation. So, this also we have discussed. Now, let us see the implications of these circular points with respect to the properties of a conics. As you know, circle is also a conics. Okay? So, how do we represent a circle? Say, if I consider, so let us, this is a property I just mentioned, that circular point is the fixed point of this similarity function. Since circular points are a point at line at infinity, so after transformation, it will be a point in the, you know, vanishing line. So that is also one, you know, should note. Now, every circle, this is the property, every circle intersects at these circular points. Now, this is a very interesting property. Let us try to understand what it means. Now, when you are considering a representation of a circle in the projective space with the homogeneous coordinate system, what we can do, we can consider the coefficients of x1 square and x2 square, they are same. And you can see that the other thing is that the product of x1 and x2, that remains, no, there the coefficient of x1 and x1 into x2 should be equal to 0. That is how the circles are characterized. But you have the other coefficients d and e and f. You can understand that x3 is the scale value. So, this is the representation of a circle. Now, if I set x3 equal to 0, which means if I consider any point in the form of, say, x1, x2, 0, suppose it is in the circle, which means I am considering the intersection of a circle with the vanishing, with the line at infinity. So, if I consider that, then actually the solution, so what are the points which will be, you know, on the circle, they would satisfy this point equation, x1 square plus x2 square equal to 0. And you can observe that both these circular points, they are satisfying this equation. So, you take I, so the value is x1 is equal to 1, x2 is equal to I is root over minus 1. So, which means x1 square plus x2 square equal to 0. So, 1 plus, you know, minus 1 root over minus 1 whole square equal to 1 minus 1 equal to 0. Okay. So, in the other way also 1 minus I 0 is also a solution. So, both of them. So, are the point of intersections. So, which means that for any circle, it intersects the circular intersects the line at infinity at I and j, which are the two circular points. So, this is a very interesting property, and this could be used in many cases. As you know, 2 points, they can define a degenerate conic. 2 points define a degenerate. So, if I consider 2 point, now this 2 point itself a conic. So, the function c which satisfies these 2 points, that could be a conic. Now, how that c would be computed? Suppose these points in the projective space, we call this point is x and this point is say y. Now, you take the points x y transpose and then x transpose, you take x y transpose and then y x transpose, because you have to get 3 cross 3 matrix. Say x is the dimension of x is 3 cross 1 and y transpose is 1 cross 3. So, you have to get 3 cross 3 matrix. Now, this is defining actually these 2 points, this is defining actually line conic. This is defining a line, because you take any point which is passing through this point, any line passing through this point. Say this is L1 and say this is L2 passing through this line. So, if I use for example say L1, so I can write it as we can write that, you can write in any way, say you can write say for example L1 say this and L1 transpose say L. Now, just multiply them. As you know, L1 transpose x, since x is lying through L1, since x is lying through L1, so L1 transpose x, this becomes equal to, this is 0. This is 0, and if I use L2, we can if I use this is also L1 transpose. So, similarly x transpose L1 also, this is also equal to 0. So, both will be equal to 0. So, that is why it is satisfying this equation. So, in this way you can show that any such line passing through these points will satisfy this. So, using that line envelope by defining this point of contact. So, x y is defining point of contact. They are not directly satisfying any point conic, but they are satisfying the conditions of a line conic. Now, that is the degenerate case. So, you have this dual line conic, it is a degenerate, means it is a singular matrix. It does not have an inverse, because in this case you do not have the point conic, you can define on the line conic. So, when we have 2 points, you can define a line conic. When you have two lines, you can define a point conic. That is the idea. So, if you have 2 lines, then the conic which is touching these 2 lines, that is the point conic. Okay. So, from there you can define also the point conic. Those points would be defining the point conics. So, if I have 2 lines say L M, in the same way I can write L M transpose plus M L transpose. I can write this. So, that also will give me a degenerate conic. Again, single point also will give me a degenerate conic, and single line will also give me a degenerate conic. We have discussed these things during the case of projective geometry. So, the property of degenerate conic is that the conic, the matrix C which is representing the conic, that would be singular, because it does not have its respective inverse. So, that for point degenerate conic we should not have its dual conic, and dual degenerate conic we will not have its corresponding point conic. Now, let us now bring it to the case of these ideal points, which defines a particular type of dual line conic, because these are the points. So, they define this dual line conic. So, if I perform this operation, algebraic operation, now the structure of the conic would be like this, which looks very simple. You can see that this part is a 2 cross 2 identity matrix, but the rest of the things are 0. So, this is a degenerate case. If I take the determinant, it would be 0, and this is what is a dual conic at infinity. We call it dual conic at infinity because, as you understand, these 2 points which are defining it, those 2 circular points, they are also point at infinity, their scale values are 0. Now, what is interesting is that since the circular points are fixed points of similarity transformation, so for similarity transformation, the transformation of this dual conic at infinity will be also preserved. So, if I have this transformation, you note that this is the transformation of a dual conic under the transformation Hs, and if Hs is a similarity, still you will get the dual conic. You can also see mathematically, this is happening here. If I use the similarity transformations, it will also give me this, that can be shown. So, which is also another kind of invariant of similarity, which we have not mentioned earlier, because we have not discussed this part, and this can be used effectively to make another kind of correction for angle preservation. So, first let us try to understand that how the angles are measured and how the dual conic at infinity plays an important role in transforming the angles or relating the angles from one space to the original space to the transform space. Now, before that, a few features of dual conic at infinity you should note, that degree of freedom of the transformed dual conic is 4 and its determinant is 0. So, this is because the similarity transformation has the degree of freedom 4. So, if I apply a similarity transformation because with degree of freedom 4, so similarly the transformed dual conic has degree of freedom 4, and we know that its determinant is 0. And the other thing is that since that this conic has the line at infinity, it is lying there, it is defining the line at infinity. So, line at infinity is a null vector, that is the point of singularity for the dual conic. That is another feature, null vector here. So, which means that if I use the dual conic and line at infinity is 0, 0, 1. So, you will find that all are 0. You can just observe that. So, what are the implications? The implication here is that suppose instead of similarity I perform any other transformation. Suppose I perform any other projective transformation. So, then this dual conic, at infinity is transformed under this transformation following the same rule. But what happens, since this is not similarity transformation, it will give me another dual conic, which is not equal to the dual conic at infinity, which is not in this shape. So, I will say it will give me another dual conic, say star, just another dual conic. Just to write something, I will write also this prime dash, just to show that it is a dual conic, transformed dual conic. But the fact is that since this conic is singular, now this transformed conic is also singular. That is the first thing. So, these properties are this singularity property, the determinant is 0, that is also true here even after transformation. The other thing is that since its null vector, the null vector of this conic is the line at infinity, say 0, 0, 1. So, the null vector of this dual conic, transformed dual conic is also the vanishing line, because under transformation this becomes vanishing line is 0, 0, 1. So, null vector of this dual conic will be the vanishing line. So, these are very interesting things that you can very easily relate from this kind of properties that we discussed. We will see that how this could be used further. So, now let us consider the fact, consider the other major type of issue. What I was discussing, that these concepts are useful when we try to relate the angles during transformation. So, first let us understand how angle is measured. Say this is a projective space, and where you have two lines, and you see that this is a line M and this is a line L, and you know that each line in the projective space representations are represented by these three parameters. First two one, you know that they are giving you the direction ratios, that is the line direction ratios, and the last one is just that if I have the line equation L1, L2, L3 can be written as L1x, L2y plus L3 equals 0. So, the first two contributes to the direction ratio. If I consider the dot product of these two vectors L1, L2 and M1, M2, then I am getting the normal. So, which means a dot product is, say I am taking two vectors L1i, L2j and say M1i plus M2j. So, if I take dot product which is L1 M1 plus L2 M2 and then take the normalize by their magnitude, because this is a dot product of unit vectors, that would give me the cosine of the angle subtended by these two vectors. So, the angle between two lines, they can be also expressed in this form. So, this expression can be simplified, can be represented in this form also. You note that this part, particularly this numerator, is written in this form L transpose C infinity star M, which means I have L1, L2, L3 and then C infinity star, which is 1 0 0 1 0 0 0 0 0 and then M1, M2, M3. If I do that, this should be equal to L1 M1 plus L2 M2. So, this numerator can be represented in this way. In the same way, now if I replace M1, M2, M3 by L1, L2, L3, so you know that this becomes L1 square and this becomes L2 square. So, I can write this and this. So, now you can see that the angle between two vectors, that can be easily expressed in this form. Angle between angle between two lines can be expressed in this form. Now, suppose I have transformed this one. If I have transformed in the transformation, what happens? This L becomes H minus T L under transformation H, and this M becomes H minus T M. So, what we can show that this is invariant under homography, which means this cos theta is invariant under homography. How? Suppose this is this transformed dual conic. This is the transformed dual conic at infinity under H, and this is the transformed line under H, and also this is a transformed line under M. So, if I compute this value, I will still get this one. So, this gets preserved, this gets preserved. So, if I take this L, so this would be L once again, and if I take this M, this will be M. So, which means in general this is preserved. So, the cos theta, so the angle, this cos theta remains the same, right. So, once this is obtained, then Euclidean angle could be recovered, which means I can compute the cosine of the angle. I can compute the cosine of the angle of two vectors and cosine of the angle of the original angle, that means the transformed angle. So, here cos theta means not the new theta prime, Here the cos theta means it is the angle of the original space. So, cosine of that space with this computation still remains the same after transformation. That is the interesting part. So, in this way you can recover the angle. But another particular fact which is also which we can notice that if L and M are orthogonal, naturally cosine of that angle forming those two lines, which is 90 degree, would be equal to 0. So, this value is equal to 0. So, this is also true in this case. Now, this is not equal to the dual conic at infinity. It is a transform dual conic at infinity, and this transform dual conic at infinity, if we can compute, then actually we can apply this property there also. So, what would be our objective? That if I have the transformed space, once I get the transformed points, from there can we estimate this transformed dual conic at infinity, and if I get that estimate, then I can get the angles between these lines. So, how do you estimate this point? So, we will apply once again like the affine rectification. Here also we will consider the pairs of perpendicular lines. So, the pairs of perpendicular lines, they satisfy this property. So, if you have two perpendicular lines, then L transpose this transformed dual conic at infinity and M, that should be equal to 0. So, it gives one equation. So, you have how many elements here? You have effectively you have 9 elements, but you can reduce it into 5 independent parameters in this space. There are 5 independent parameters. So, this equation can be written in the form of 5 independent parameters. You consider one of the coefficient, set it to equal to 1. Otherwise, again you have to use the set of homogeneous equations. So, either 5 independent parameters or 6 dependent parameters, by which you can express this equation as a linear equation, from one constant. So, if I have 5 such constant, so I will get 5 equations and I can solve for the 5 parameters. But as you know, seen this particular matrix, its determinant should be equal to 0. So, that is also another constant, which is rank deficient matrix. So, in this method, what I mentioned, you are not really recovering the rank deficient matrix. So, what you can do to make it rank deficient, you can perform singular value decomposition and you can make it a rank deficient matrix. So, just let me give you quickly the overview of this technique. Say, as I mentioned, that we will be using the property of orthogonal lines, and two orthogonal lines L and M, they satisfy this constraint L transpose C infinity star prime M equals 0. This is the equation. So, minimum 5 such orthogonal pairs are needed, and a typical equation would look like this. So, actually this C has been expressed as a column vector. So, C has been expressed as A, B, C, D, E, F in this form with the parameters, and then we have formed this equation. So, where C is representative, as I mentioned, this C is not the 3x3 matrix, and then these are already known. This is the equation. So, you can apply direct linear transform least square error method, which we have discussed earlier, to solve a set of homogeneous equations to get C. That means, if you have more number of observations, you require minimally you require 4, but we will be having more number of observations here, actually 5 I told. So, more number of observations, and then what we can do, that we try to so if this matrix, so we get a matrix here, we express this as a stack of matrix A, C equals 0, and as you know that your objective is to minimize this norm AC, minimize this norm AC equal AC and AC square. So, which will be giving you a solution if I take the covariance matrix and compute the covariance matrix and take the eigenvector corresponding to the minimum eigenvalue. So, eigenvector corresponding to the minimum eigenvalue, that would be the solution. So, from there, no, it is a 6, no, because it should be 6 dimensional. There are, this matrix would be 6 cross 6 matrix, A transpose A. So, 6 dimensional, no, eigenvector, and from there you can form the matrix C, and then you perform the singular value decomposition, and since it is rank deficient, so the smallest singular value you set it to 0. By estimating transformed dual conic at infinity, what we can do, we can perform another kind of rectification on the images, and this time we can make equivalent transformations as a similarity transformation, because what we can consider that suppose I have an image and I have the transformed image. Say you have an original image and you have a rectangle here, and then you have applied some transformation H, and this is a perspective transformation. So, you know that this rectangle could be just a general quadrilateral. Now, we understand that if this transformation was a similarity transformation, then actually this dual conic at infinity would have been preserved. So, for a similarity transformation, for a general transformation it is like this, but for a similarity transformation still this rectangle would look rectangle, and also it will keep the aspect ratio, that means proportional sides would be of the same proportion. That is for similarity. Now, the question is that can I get back this one? So, if I can get some estimate of H, then by applying H inverse we can get these things. So, what we can do, first we can form the dual, we can estimate the transformed dual conic at infinity and up to similarity it says, which means that if I apply this, it can be also, it may not exactly come here, it can come here, you can get this result. So, aspect ratios will be preserved, exact distances between vertices will not be preserved. That is the up to similarity you can do this kind of rectification. So, once you estimate the transformed dual conic at infinity, the thing we discussed just before this slide. So, what you can do then, we can make factorizations in this form. So that what is, so that say this is, say in a factorization this matrix is the dual conic at infinity, which means this should be in this form 1 1 0 0 0 0. So, this is the form, we know that this is a form of dual conic at infinity, and then if I apply this transformation H, then the dual conic at infinity, transformed dual conic at infinity would be like this, and which is estimated from this image. So, our problem would be, computational problem would be how to estimate this H. So, if I factorize it, then from that factor itself we can get. So, one simple way could have been that perform this singular value decomposition, and we know that this is a rank deficient matrix. So, in singular value decomposition you can get the singular values, say in this form, say you can get some singular values, say lambda 1, lambda 2, this is a diagonal matrix, and since this is symmetric you will get U transpose. Now, your objective is that to make this lambda 1 1 and to make this lambda 2 1. Now, with some scale adjustment that you can do, with some scale adjustment you can bring these two in such a way that they would be, so that means you multiply the first row, first column here with root over lambda 1, and the same thing would be multiplied there. Similarly, the second one would be root over lambda 2 and same thing, and then that would be absorbed. So, essentially it means that you can always perform for a rank deficient matrix, you can do that thing, you can make this transformation in this form. So, now you can see that this u could be equated with this h. So, you can get an estimate of h, and once you get an estimate of h, apply h inverse on the image, that means the inverse transformation, and you can get back the respective configuration up to similarity, which means once again the distances are not preserved, but aspect ratios of those things are preserved, angles are preserved. So, this is what you apply H inverse to the image. So, just to summarize that the things what we covered under the topic of projective transformation, what we discussed, this is the third lecture in this topic, that first we considered the definitions of a projective transformation, where it has to be a transformation between 2D projective space to another 2D projective space. It should be invertible and it preserves the collinearity, and its form is always linear, which is a 3 cross 3 matrix form. And there are mathematical relationships related to this transformation of point, line, conics. Say point is transformed just simply multiplying by this transformation matrix, and also the line would be the corresponding transformation, a transpose of H inverse. So, I think we have discussed somewhere else, we will come to that, and conic also could be transformed. One of the computational problem, what we can see, that if I give you two projective spaces, so when I get two images of the same scene, again this is a projective, we can consider them as two projective space, and there is a projective transformation because if the scene is planar. Now, there could be various other scenarios of having two projective spaces where there exists a projective transformation. So, problem would be that if I give you these point correspondences, can you recover that can you estimate that transformation H? And that we discussed, and we have used the direct linear transform method. First thing, the minimum 4-point correspondence is needed for any general projective transformation, but there are special cases, like for affine transformation, projective transformation, you require minimum 3-point correspondences, and for similarity transformations you require 2-point correspondences. So, this is a method of direct linear transformation that we have used, and use of linear transformation of points to make the computation robust. So, for that estimation we have applied linear transformation, and from there we made our computation robust. Then there are various transformation which goes through under homography, as I was just mentioning, that point of course transform to a point, and this is a relationship with respect to projective transformation H. Similarly, for line also it transform to a line, and under the projective transformation H you have to then consider transpose of H inverse as a transformation from line to line, and a conic it's transformed to another conic, a point conic is transformed to another conic, and this is the expression, and even a dual conic, that is also transformed to another dual conic, and this is the expression, and these are consistent. So, the point conic and dual conic in the original space, they are transformed again to the point conic and dual conic conic with the same consistency. Then the existence of linear groups in projective transformation is projective linear group, it is a linear group there, and then its different subgroups, and we have discussed about the hierarchy of this group, like you have projective linear group which has 8 degrees of freedom, then affine group which has 6 degrees of freedom, and Euclidean group which has 4 degrees of freedom, and oriented Euclidean group which has 3 degrees of freedom. Conic dual to circular points are interesting concept, particularly when we are trying to estimate the angle between two lines and also performing the rectification process, rectilinear rectification. First thing, it is invariant under similarity transform, then its line at infinity is a null vector of this conic dual to circular points or conic dual at infinity, and then it preserves the cosine of angle of two lines under transformation. So, this was the expression that we have considered, and using homography we can perform different kinds of rectification. One is affine rectification, And another one is stratification, which I discussed in the last, which is basically a recovery of metric properties, because it is similarity transformation, under similarity transformation, so the distances become proportional under that transformation. So with this, let me conclude this topic, and I thank you for your patience and listening.